Hello everyone, and welcome to the fourth day of our tutorial series on the C programming language. I see that we've already got some people in the chat. BlueJay, TT Viewer, Sarlivia, TG1802. How's it going, y'all? Hope that y'all are having a good day so far. Had a good before noon. Yeah, yesterday was a bit of an interesting day for all of us here in the U.S. It's going. That's a fair description of most days, to be honest. yeah, no, I feel ya. But yeah, it was a bit of an interesting day, but I'm glad that we are all still able to be here and provide the constancy that is the relatively unchanging C programming language. So yesterday we dove into a lot more about how we might use pointers in our C programs. We talked about some kind of caveats that apply to the usage of pointers, namely the fact that we can do math with pointers and that math doesn't quite work like it normally does. Remember, if we add 1 to an integer pointer, we actually move the address by 4, which seems to violate the very fundamental foundations of math, but it does help us when we are traversing through arrays, which is the next thing that we talked about, and how arrays in C work really differently from arrays in Java that we're used to, right? That they don't store size, they don't have any methods defined on them, and really, arrays in C are nothing but pointers to contiguous memory regions. And so when we pass an array to a function, that array actually decays down to a pointer. And then the one other thing that we talked about is we talked about strings, which are essentially character arrays in C that are terminated by a null character. And that's most of what we discussed yesterday. And today we're going to go a little bit into, now that we've learned about really all of the fundamental types in C, we're going to dive into how we might combine those types to create new data structures in C. But before we do that, I do want to show you one more type of pointer. And I've saved this one for last because A, it's the one that you might see a little less frequently, and B, because the syntax is very strange and kind of confusing. So we're going to begin today by talking about function pointers. Now previously, the pointers that we have been working with, let me increase my font size here so we can see it. The pointers that we have been working with pointed to data. They pointed to data that we ourselves initialized largely on the stack, and sometimes in static storage space. But yeah, usually it was data that we had initialized ourselves. Function pointers, on the other hand, are, like they sound, pointers that point to functions instead of data. And so you could argue that, in memory, technically everything is data. And so as a result, having a pointer to a function is not inconsistent, but it is a little bit different, partially because most operating systems will treat code and data a little bit differently, but also because when we have a pointer to a function, we can call that pointer to execute the function. And so let's go ahead and learn about function pointers by extending this little array program that we wrote yesterday. So just a recap of what this program does so far is that we are instantiating a 64-element array on the stack called R. We're looping through the elements of that array and setting each element to its index, and then we're calling this function printArray with the array and its size, because remember, when we're working with arrays, we have to pass the size, and then we're just printing out all the elements in the array. So what we're going to do now is we're first going to add a comment to tell us what we're actually doing. But now what I would like to do is write a very common functional programming idiom in C. And more specifically, we are going to write the map function in C. So this is the function, if cline will respond there we go, map. We're going to take in an integer array. It's obviously going to have a size. And then we're going to take a function that's going to manipulate this array. So if you're not familiar with what map does, it essentially iterates through the elements of an array and applies a function to each array, yielding the new array. Now, for our purposes, we're actually going to manipulate this array in place, because we haven't quite talked about how we can return an array from a function yet, and that's something that we're going to get to at the end of today. But for now, we're going to manipulate this array in place. And now what we want to do for our map function is we want to have a very, very simple transformer function that takes in a single integer, right, a single element of our array, and returns a new transformed value. And the way that we're going to write that is as follows. So function pointer syntax in C is extremely weird. What we write is we start off by writing the return type. So we write the return type. We then write, in parentheses, pointer, the name of the function, and then we list the arguments. And when we list these arguments, we're not going to list names for them, we're only going to list types. So in this case, if we want a function that takes in a single integer and returns an integer, we would write that type as follows. We would write int, pointer, name of the function. So I'm just going to call this function transform. And that function takes a single integer argument. So yeah, a little bit odd in how we do this. So this in Java would be equivalent to, what do they call these things? This would be equivalent to, I think, just like a function of int. I'm not too familiar with the Java functional programming interfaces. I haven't really used them too frequently, and when I do, I usually look them up. But yeah, so it's equivalent to passing a function. And now, in C, if I want to call this function, and now that I have declared it as a function pointer in the arguments to this function, I can actually just call it like any other function. So, if I want to apply transform to all elements in my array, then what I can do is simply loop through my array, just like we did before. Oops, our size. And all I have to do is say r and I equals transform of r at I. And so you see, we can call our function pointer just like we would call a normal function. So yeah, so this is function pointers in C. And there's not really a good intuition for this syntax. It's really just something you have to memorize. And quite honestly, it's something that I have to memorize or rememorize every time I'm doing something that works with function pointers, because we don't use them too frequently. And yeah, whoever came up with this was not really exercising their language design muscles that day. But yeah, so now if we run this, if we try and call this function, we have to actually, define a function that we want to run when we call transform. And so in Java, you might be familiar with the concept of a lambda function, or an anonymous function that we didn't have to give a name, and we could just, execute some code. So in Java, if I wanted to call this function, then I'd do something like this. I would pass, my array, and pass the length, and then I would pass a lambda that might look something like, let's say we want to multiply everything in the array by 2, I would pass a lambda that looks something like this. In C, we do not have anonymous functions. So yeah, the C language just completely lacks anonymous functions, and there are some good reasons for that. If you're familiar with C++ lambdas, and the fact that they're the only programming language construct I've ever seen that uses all 3 of the brackets, because sure, you'll learn why C might not have anonymous functions. But we can work around this very simply by saying, okay, well, I need a function, and I would like that function to be allocated in a way that I can get at it using a pointer, so I'm just going to declare it at the top level of my program. And so I'm just going to write my transform function just like I would any other function. And so here I'm just going to write a function called mul2. Oh, that's a terrible name. Let's call it double because, oh, right, we can't do that. Okay, fine, mul2 it is. And we're going to have it take a single integer. And this function is just going to return val times 2. And so yeah, all we're doing here is this is equivalent to this lambda x into x times 2. That's all that this function is doing. And so now, if we go down here to our main function, then we can call this. And I can say, okay, now I want to apply mul2 to every value in my array. So I'm going to call map. I'm going to pass it my array. I'm going to pass it the size of the array, and remember that we had defined that as a constant, just because that's typically what we'll do in C programs. We'll define the sizes of our arrays as constants, just so we don't have to keep typing them, and to make refactoring easier. And then to pass my function pointer, all I do is type the name of the function. So this is another slightly odd thing about function pointers, is that you may say, well, hey, wait a second. Previously, when we wanted to pass a pointer to something, I had to take the address of that thing. And you actually can do that in C. You can take the address of a function and it will work. But as some syntax sugar, the C compiler understands that if you are trying to pass a function as an argument to another function, you want to pass a function pointer, and so it will automatically convert that to a pointer for you. It's just a little, again, it's a little nice feature built into C that helps to make our programs a little bit shorter. And so now if we go ahead and call this function, we call map with mul2 and we print our array, we should see that each index in our array contains the original value, so the index times 2. And if we run it, then we'll see that that is the case, right? 48 times 2 is indeed 96. 50 times 2 is 100, and so on. And so there you go. So that is the usage of our function pointer. We declared our function, which in C we have to do out of line. We have to do it as its own function, just because that's how the grammar of the C language is defined. We pass that function to our higher order function map, our function that takes a function pointer. And then here's our function pointer itself, and then we call that function to manipulate the values in our array. It's relatively straightforward. It's not the most difficult concept to wrap our heads around. I just really wanted to highlight this today because the syntax is really wonky. It's very strange. And also because a lot of people try and immediately go, they see a function pointer and they go, oh, C has lambdas. That's interesting. I didn't know that C had lambdas. And the fact of the matter is, unfortunately, C does not have lambdas. C has function pointers. They are very different. A lambda in most programming languages is actually what we call a closure. A closure, not the programming language spelled with a J, a closure, C-L-O-S-U-R-E, like this in the chat. A closure is a function and its environment. So that would be something like how in Java, let's say that instead of multiplying x by 2, I wanted to multiply it by some variable called factor that I had in the current environment. In Java, this would be a perfectly valid closure definition. Again, lambdas being closures, we can consume some of the surrounding state. And at C++, its weird lambdas work in the same way. Oh, and hello, XISZ. Welcome back. The cake is indeed a lie. I haven't played Portal, but I've heard it's pretty good. I should probably get around to that at some point. But anyway, the reason why C++ has these weird lambdas that, you know, look like an eldritch horror is that some of this syntax, namely the square brackets, define which variables should be captured into the closure environment. And, you know, we can do weird things like capture everything by value, capture everything by reference. We don't need to worry about all of that. But in C, we just plainly don't have that ability. And so if I tried to define this function and use some values from a surrounding environment, that wouldn't work. right? Partially because C just doesn't give us the ability to define inner functions, so this is an invalid declaration if I try and declare a function inside another function. But also just because, yeah, C does not natively provide support for closures. And so we're going to stick to the essentially pure sense of a lambda, a function that is invoked, takes a single argument, well, or multiple arguments, it can't take multiple arguments, but takes some arguments, outputs a value with no additional context. And now, if you did want to pass an additional argument to this, so let's say that you did want to pass, let's say that you did want to pass a factor to our multiplication function, you could totally do that, but you would need to add another integer to our function pointer, and then probably you would need to also add that factor as an argument to our map. And so you see that C function pointers are less flexible, but this also operates, these function pointers operate at a much lower level of abstraction than the closures in other languages, and so that's why, you know, it's a fairly good fit for C. And we had a question in the chat from Prince Logic, ampersand in C++ means reference, and in C means address. Yeah, so in C++, they just decided that they were going to define a third type that looks like this. So this would be an integer reference, where we follow the type name with an ampersand. And a reference in C++ is a pointer that you don't have to use pointer syntax with. And so if you assign to a reference, that's equivalent to saying, you know, the value of your reference is equal to the thing that you assigned. And so, yeah, it's a pointer without pointer syntax. It's just an additional feature of C++. We don't have them in C, and I'm not going to belabor that too much. But yeah, of course, in C, anytime that we prefix something with the ampersand operator, that means that we are getting the address of that value, as you mentioned. So yeah, small difference between the languages. And we're going to stick with the C one today, because it's much less complicated, and that means I don't have to talk about reference semantics for the remainder of my life. So, yeah, that's function pointers. That's really all we need to know about function pointers. You can do cool things with these. You could store them in arrays if you want, right? So we can make an array of functions and pass that array and execute that array of functions on a list of values. But in general, C programmers don't gravitate towards this kind of functional programming approach to doing things. You don't see a lot of higher order functions in C. And the reason for that is really just that they're kind of a pain in the butt, and because we don't have things like closure capture and currying and things that make functional programming advocates, you know, people who like functional programming like myself, really happy, C doesn't feature any of that. So typically, we'll just stick with our good old classic imperative loops. But these are good to know, and we will actually see them when we start talking about our next topic, which we're going to move on to now, which is structs. So, previously, we have discussed variables in isolation, right? We have talked about how we can have single variables in C. We've talked about how we can have kind of aggregates of values in arrays, but we haven't really discussed how we can potentially make data structures in C. And so what we're going to do today is we're going to start off by talking about the way that we make data structures in C. So in Java, if you wanted to make a data structure, it was a fairly simple process. All you did is you said, okay, public class structure, and then you define some instance variables, right? So you know, private int v1, private int v2, or private double v2. And you define a constructor, you know, that might set these variables to something. And that worked great in Java. However, as we've mentioned before, C does not have classes. We do not have this concept of a class in C, of having a data structure, right? A grouping of data that can also contain things like functions, or methods that are executed upon the structure with the structure as their environment. We can't have things like polymorphism, or inheritance, and so yeah. So we're going to talk about how C does data structures today, and it's actually a lot more simple than it is in Java. because it has less features. But hey, we'll take simplicity where we can. We've been talking about pointers for the past few days, so we'd like something simple. So in C, we declare a data structure using a keyword called struct. So we declare a data structure using the struct keyword. And we follow the struct keyword with the name of our data structure. And BlueJ, it's not really an array. It's a lot more like a class with a bunch of accessors. But yeah, so a struct, yeah, and then we'll give it a name. So let's say that, just for the sake of argument, we are writing a struct that can store some information about a student. So a struct that can store some information about a student. And now I will note just a brief naming convention here. In C, by tradition, we name everything lowercase snake case. This was a comment that I got on the YouTube video of a previous day. Yeah, we name every variable that we write really lowercase snake case, meaning that if this had, multiple words in it, we would say something like, student data with an underscore in between. This includes structs. An XISZ, you mentioned type defs, and we'll talk about type defs. And we'll talk about why I actually don't like using type defs too much. But for right now, let's just stick with the very basic kind of struct definition. And so another thing that we have to note about structs, and the thing that drives a lot of, especially, newer C programmers insane, is that struct definitions, unlike function definitions, must end in a semicolon. So after the closing brace, you have to have this semicolon, otherwise your compiler is going to yell at you. So yeah, in C, structs are not really top-level declarations. They can be, but they also function like statements, meaning that a struct definition must end in a semicolon. And now within our struct, we define the data members of the struct. This is equivalent to our instance variables. It's the data that we're going to store inside the structure. And so, what might a student have? Well, a student probably has a name. So we'll give them a string name, right? A char pointer, just being a null terminated string. What else might they have? They might have a student ID. And let's say that at our imaginary university, student IDs are integers. What else might our student have? Our student probably has a number of credit hours, right? And that would be an int. A student probably has a GPA. And yeah, campus ID, yep, we've already put that. BlueJ, an int val for motivation. I mean, given the online semester, I'm not really sure that I want to actually peg a value in our struct to 0. That's kind of something that we can just imply. So yeah, maybe we don't store that in the struct, but we can substitute it into any formulas that need it. Campus ID, yep, we've already got that, int ID. And let's say that since this is an American university, we'll define a double for their loan. And, actually thinking back on university tuition, we better make that a long double just to be safe. Okay, and there we go. So yeah, let's say that this is our basic definition of a student. So now the next thing that we want to do is we want to actually make a student. And we're not going to do this the same way that colleges do in that we're just going to mail out a whole bunch of crap mail to you for like 5 years and assume that you're going to come to our university. We're going to learn about how to declare structs in C. So the simplest way to declare a struct in C is as follows, where we say struct student. So here we're, and then I need a name, right? So I'm going to call this test student. And note the type here. The type of a struct variable in C must include the struct keyword. So in C, structs exist in a separate namespace from variables. So what that means is that if you want to have a struct variable, then you need to precede the type with the keyword struct to indicate to your C compiler, hey, this isn't a built-in type, this is a struct type. I'm gonna turn this song down a little bit because this pianist is really going hard. So anyway, and now that we've got some space allocated on the stack for our student... Oh, Inscript Tech, am I drinking out of a beaker? Yes, I am. They make really good cups. They're really hard to knock over. They're heat resistant. They're chemical resistant. They're great. Thank you for reminding me to hydrate. So anyway, now that we've allocated space for our student on the stack, we're going to assign our instance variables, or our, what we call members or fields in C, instance variables in Java. So what I'm going to do is I'm going to say that the name of this student is going to be, you know, test student. And you'll notice that the way that we accessed this, this field is exactly the same way that you might have seen us access Java instance variables. We use the name of our struct, or the name of our variable, then dot, and then the name of the field. Oh yeah, and let's get in Java classes, the naming convention is that you capitalize the first letter. And yeah, that's not the same for C. In C, all identifiers begin with lowercase, and we use snake case to separate words. So if this were actually called student data, then we would have an underscore between the two words. So yeah, we're going to stick with all lowercase in C. Oh, and Prince Logic, can you use right arrow instead of the dot operator? That means something different. The right arrow means something different, and we'll get there when we talk about pointers to structs. But for now, we've just got a struct locally on the stack. So yeah, we're just going to use the dot operator, which means I've got a struct. I want to access one of its members. We use the dot operator. And so now let's go ahead and just fill in the rest of these fields. So teststudent.id equals, I don't know, 1, 2, 3, 4, 5. Teststudent.credit hours equals, let's see here, how many credit hours should they have? We'll give them 40 credit hours. Teststudent.gpa, we'll give them a 4.0, I wish. And then, of course, the amount of loan that they have will be, oh, I haven't included what I need to type infinity, so we'll just go with a really big number. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 87 cents. Okay, great. So here we go. Now we have defined our struct. Oh, and yeah, let's get, this is clearly a US student. Oh yeah, that's why we've used long double for this type. We definitely need some more precision and some more value space. And Inscript Tech asks, what keyboard are you using? Yeah, that's a good question. This is a IBM Model M from 1990. So we've got a retro keyboard here, a keyboard that's older than me. And it's got these very nice clicky switches that make all kinds of crazy noises when you type on them. It's fantastic. But anyway, now I would like to actually see the values in my student. And so what I'm going to do is I'm just going to write a function here called student report. And this function is going to take a pointer to our student. And so yeah, so we're going to take a pointer to our student. And the reason that we are going to take a pointer to our student relates to the fact that in C, all variables of any type are passed by value. And so as a result, if we try and just pass this struct student, then we're going to copy all of this data, right? All the data stored in our struct to a different location in memory so that we can execute this function student report. And that is pretty costly. And so what we need to do then is we need to specify that this is going to be a student pointer so that all we're doing is passing the address to our student and not the entire struct, not all of the data in the struct. And Lusket has predicted what we need to do. Yeah, now we need to pass the address of the student. So when I call student report, I'm going to need to take the address of test student. So now I'm saying I'm creating a pointer to my student, right? We can read this type just like any other pointer, pointer to struct student, and I'm passing the address to my student variable. Okay, great. So now let's go ahead and print some information about my student. So let's see here. I'm definitely going to need standard IO for this. So let's hash include, stdio.h. Lovely. And so now let's go ahead and write this function. So what I'm going to do is, let's see here. My student report's going to look like this. I'm going to printf the student's name, and then their ID. Oh, InScript Tech, thanks for the follow. Yeah, this should be, yeah, hopefully this will be a pretty fun series. Yeah, we're pretty much covering the entire C language. So yeah, hopefully you enjoy it, and yeah, thanks for the follow. So anyway, yeah, so we've got our printf statement. We're gonna go ahead and print the student's name, then their ID, and then we're just gonna go ahead and print all of the other information about them. We're going to print their number of credit hours, %D, their GPA is a long float, and then their loan will of course use the US dollar symbol, is a long double, and then we'll just pass in variables name, ID, oh, sorry, S name, S ID, S credit hours, S GPA, and S loan outstanding. Oh, hello. And we don't like this type because, oh right, it's not LLF, it's capital LF. There we go. So, some new syntax here. Now that we have a student pointer, we can no longer just access the name of our student. If we try and do this, then we get a warning that says member reference to type struct student is a pointer, telling us that, hey, you cannot access pointers, or you cannot access members of structs passed as pointers using the dot operator. We instead need to use this funky looking arrow operator. And Divi4K asks, what's the arrow symbol? And yeah, this is the point at which I should probably disable font ligatures in my editor. So here you go. So this might be a little bit clearer now. It's just an ASCII art arrow. It's a hyphen and then a greater than sign. And what this does here is it says I have a struct pointer and I want to access a member of the struct that is pointed to by that pointer. So this syntax here, where we say, you know, S name is equivalent to saying the value of S dot name. Right, so it's basically syntax sugar for this operation, where we're saying that we're going to get the value of this pointer, right, or the value at this memory address, which happens to be our struct student, and then we're going to access their name field. And so yeah, so this arrow operator is just shorthand for that. Anytime you've got a struct pointer, just go ahead and use the arrow operator. I've seen some people try to staunchly stick with this syntax because they just don't like the arrow, and that's, no, just use the arrow. It's much more convenient, and it's very standard amongst C programmers. XIS said it's basically pointing toward the object of student. Yeah, it's basically pointing towards the, you know, quote-unquote instance of our student that we have. So we've initialized this student on the stack in our main function, and then we've passed a pointer to that student to student report. So we've just gotten the memory address of this student. And so we're passing that memory address, and so we can access its fields using the same offsets that we accessed them in our main function. And we'll actually discuss how this works. It's actually fairly interesting. Your C compiler does a lot of work. It does a lot of work to make sure that structs behave correctly on different platforms, and we'll talk about that. But first, we've got another question. Can structs have methods inside them? Yes, kind of. Structs can have function pointers inside of them, but they cannot have methods. So yeah, so we cannot have an actual method, meaning a function that captures the struct environment inside of a struct, but we can have a function pointer that takes a pointer to the struct that can then access it. And that's kind of how we emulate object-oriented programming in C. But yeah, so this little symbol right here, just dereference and member access. That's all that is. So now if we go ahead and we run this program, then we should see a representation of our student printed out to the console. And there we go, we do. So you see, here we go. So test student ID 12345. They've got 40 hours, GPA of 4.0, and a loan of more money than they'll ever earn. Perfect. So, oh, and we have, of course, not been the best of C programmers. Let's go ahead and be good boys and girls and return exit success. Variable, there we go. Okay, great. And so here we go. So this is how structs work in C. We can actually summarize it in one page of code, which is cool. However, there are a few things here that are, a little annoying, right? There are a few things that we really don't like as much as we might in Java. The first one is the way that we initialized our struct. Holy crap, that was annoying, right? That was really, really annoying. We had to type out test student dot every single time we wanted to assign an instance variable. And moreover, unlike in Java, when we don't, if we don't initialize something in Java, it has a value of 0. In C, if we forget to initialize a value in our struct, remember that C is not going to give it a value of 0, and so we're going to end up with some nonsense value. So we have to remember to actually assign every single struct value every single time. And that just kind of sucks. Yeah, let's get no constructors. No. Well, unless you write them yourself. I mean, you can write them yourself. And when we talk about dynamic memory, we'll get there. But yeah, so yeah, this really sucked to have to write. So let's talk about how we can make this better. The first way that we're going to make this better is through what's called initializer list syntax. Oh, A2, why didn't you type LF instead of F for the GPA value in printf if GPA is a double? We didn't have to. I didn't have to do that. I just kind of do it by convention at this point, basically that like single F is float, lowercase LF is double, capital LF is long double. You don't have to. You can just type the normal F and your compiler will figure it out. I don't know. It's just kind of baked into me to type it the long way, I guess. Yeah, you can get away with not doing it. But anyway, so yeah, let's figure out an easier way to initialize this struct. And we're going to use initializer list syntax for this, which looks like this. So we say struct student test student equals, and then we've got some curly braces, of course, followed by a semicolon. And now inside of these curly braces, we're going to write every data member of our struct in order. And so let's say that, and so let's go in order down the list. The first thing we've got in our student is the name. So I'm going to assign the name. Next thing we've got is an ID. Let's go ahead and write the ID. We've got 40 credit hours, 4.0 GPA, and an outstanding loan of... Lovely. Right, US currency. There we go, 29. Okay, cool. And so now you can see that this struct declaration, this initializer list declaration, is equivalent to this long invocation that we had down here, having to type test student dot every single time. So yeah, so this is a nice shorthand that we have that will allow us to declare our structs. And so if we go ahead and run this, you'll see, hey, our program still works correctly. All of our members are initialized to the values that we set. Which, hey, that's pretty great. This form does have some downsides, though. And one of the biggest downsides of this initializer list form is that... Oh, Lusket, can you have default values? No, unfortunately you can't. This is C, no default values. Unless, again, you write a function to provide them yourself. Yeah, I know. C++ is nice, isn't it? But yeah, nope, no such conveniences in C. But yeah, so this list syntax is cool, but it's got a few issues. The first one being, I don't actually know, reading this, what these members are. I have to go back and refer to the definition of our struct in order to figure out what these variables are. And so, to make life easier for me, I might say, okay, fine, you know what? I'm just going to comment each of these. Okay, this is the loan outstanding. This is the GPA. This is, what is this? This is the credit hours, and so on, right? And you can do that. That's kind of cool. That's a way to kind of document your code. But we do have another issue. And that is, let's say that now I've gotten an email from the registrar of this university. And the registrar of this university told me, hey, okay, I need you to store some additional data about a student. I'm like, okay, cool. What do you want me to store? And now I'm going to instantly date this tutorial by saying, okay, well, I want you to store whether or not this student has received their COVID-19 vaccine. So bool has received COVID vaccine. And I instantly go, oh, crap. You want me to... really? Oh, no. Well, that's not good. Because now, here's the thing. Let's say that, if I actually insert this member at the end, it's okay. Because if I only have a partial initializer list, all of the remaining values after the ones that I mention are going to be initialized to 0. And so I can actually just say, okay, fine, this is okay. By default, we'll say they have their COVID vaccine. That's cool, right? That works. But let's say that I don't add that as the last member. And now we have a problem, right? We've got a problem. And the IDE even tells us, hey, why are you trying to convert a double to a Boolean? And now you go, oh no, that was a bad decision. I now have to cascade this change all the way through my entire program. Every single time I use an initializer list, I now have to change it to go ahead and say, all right, fine, I'm going to go ahead and say, all right, by default, they have not received a COVID vaccine. There you go, done. And yeah, you're right, Luska, it never makes sense. Now the load is 0, and we're in the US. That ain't gonna happen. So, yeah, that's the downside of initializer list syntax. It is kind of cool in some ways, but it is a little bit annoying. And so there's a better way to do this. And now let me note before we move on that initializer list syntax is really, really useful in my opinion for one thing in particular. And that one thing is zero initializing structs. So if I want to set all of the values in my struct to 0, I type this. Struct student, 0 student, right? So here's our type, struct student, the name of our variable, 0 student, and then we're going to 0 initialize all of the members of the struct, right? We typed no members, and so all of the members after that, all of the fields after that, are going to be initialized to 0. So yeah, that's how we 0 initialize a struct in modern C. You'll see a lot of code bases that actually can't do things like this. This was a fairly recent meaning the 90s, addition to the C language. And so you might see a lot of legacy code that doesn't use this. Some of the code you might see in a C class, you might not see this. Your professor might not know about this syntax if they learned C a really long time ago. But you should feel free to use it if you have a modern C compiler. It's super duper useful. But so yeah, now let's talk about how we can actually fix this problem of the fact that I just added a member to my struct and I now have to reorder the entire program. So let's talk about how we do that. And so yeah, so let's say go ahead and go back here, delete this variable, stick with this. And Luska in the chat says, if you want to let users input the data, you don't have to save the input to temp values first. Yeah, that is kind of, that is a handy aspect of this. Yeah, you can just write your values directly in line. And you can have function calls in here too. So yeah, you could totally have, calls to functions that get user input and validate it or anything like that. Because this syntax really just expands to that syntax that we had before where we said, student dot name equals test student, student.id equals blah, 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 etc. It's syntax sugar. Again, it just expands to that same initialization form. Cyber curious, why do we put a semicolon at the end of structs? Also, when you pass the pointer, why do you say struct student? Right. So we have to say struct to indicate to the C compiler that this is not a built-in type, this is a struct type. C is a really simple language, and C compilers, at least the parsers of C compilers, are really simple in some aspects with regard to type declarations, in that we say every struct name in C will always be preceded by struct. And then they're really complicated in that they have to have non-deterministic parsing for pointers. But hey, that's programming languages for you. And Raven suggests use typedef. And well, we'll talk about typedef, and we'll talk about why I don't like using typedef. But yeah, we're not going to use typedef for now. But for now, before we get there, let's actually talk about how we can rectify this situation. Now, C has another form of initializer that we can use. It's a form of initializer that we call a designated initializer. And what this lets us do is specify the names of the fields to which we want to assign values. So instead of just saying test student, Using the same syntax with the braces, I can say dot name equals test student. Dot ID equals this. Dot credit hours. Dot GPA. And dot loan outstanding. And there we go. And that's how we use a designated initializer in C, where we specify the names of the fields to which we want to assign values. And this one is really, really useful because, as Luskett said, order doesn't matter at all. I can do this. It'll still work. I can shuffle all these fields around however I want, and we will still get the expected output. Oh, hello. What do you not like? Oh, uh-oh. Syntax error, semicolon. Oh, does MSVC, or does the version that I have this set to not support this? Uh-oh. That's not good. Let me briefly check my CMake lists. You know what? Here. Let's see if having it use C11 will help. Might be a tactical error on my part. Oh, does it not like the 0 initializer? There we go. Okay, yeah. So here we go. So now we've got here our test student, and we've got all the fields just with the values that we were expecting. But here we can list these boys in any order and it'll still work. It doesn't matter how we order them. The C compiler will arrange them in the order in which they should appear using the designated initializer. For simplicity though, typically you will see people keep them in order. It's just kind of a standard that we keep them in order. Oh yeah, and the last comma, yeah, I'll mention the final comma. So you'll notice that whenever I write these initializers, I put a comma at the end. And the reason I do that is it's not required, right? You can omit it and your program will still compile and run just fine. It's not a requirement by any stretch of the imagination. I just like to have it because if I want to add an additional field after this, right? So let's say that I'm going to add back my COVID vaccine field. If I want to then add an initializer for that variable, or for that field, I don't have to change 2 lines, I only change 1. And so the reason that I put the comma is it just makes it easier for version control to differentiate which lines have changed and which haven't. Because to add a field, I only have to change 1 line instead of 2. It's just something that I do. You definitely don't have to do it. It's personal preference, but it is kind of my personal style to always include it to make my get diffs simpler. Oh yeah, no, that wasn't what caused the compile error. It seems like the Visual Studio C compiler doesn't like 0 initialized structs. Just using the like open brace, close brace syntax. It appears that it has an issue with that. Which is really weird, but you can get around that, I think. If we just write a single 0, that should do it. Yeah, there we go. Okay, yeah. So this is another way to 0 initialize, where we just say we're going to set the first field to 0, and then all the rest will also be set to 0. Yeah, you can do this. It's another way to 0 initialize if your compiler doesn't support just doing this, which some compilers don't. Anyway. Back to this. So yeah, now, if we add our COVID vaccine field, doesn't matter. If we just want it to be false by default, we don't even have to change anything, right? And moreover, if we want to add it somewhere random inside of our struct, say we add it up here, doesn't matter. We still have the same values because we initialized our struct fields using names instead of just their order. And so yeah, so this is called a designated initializer, and this is actually why I really prefer using designated initializers instead of initializer lists whenever I can, is that they really help with maintainability, and they're actually just a little bit easier to read, right? We know what all of these fields are, instead of essentially just having to constantly refer back to the definition of our struct over and over and having to know the order in which the fields are declared. Right? I mean, yeah, like this is something that, right? It's not something that as Java programmers you ever had to do, right? You didn't need to know what instance variables had been declared and in what order they were declared. You just needed to know that they were there and that they had names. And so, yeah, it's much nicer to just have to know the names and not the order. Oh, and Cyber Yami asked, what were the includes? Our includes were, well, I had STD bool so that I could define the COVID vaccine as the bool type, but I'm going to leave that out, so we don't really need that. Let's be honest, none of us probably have the vaccine yet. And so we also have stdio, right, to give us functions like printf, putS, all of the things that deal with file and console input and output. And then I've included stdlib for the exit success macro, and then some other stuff that we're going to talk about soon. So yeah, this is structs in C. And now, something that I do want to talk about as we continue is how structs are laid out in memory, because the layout of structs in memory is actually very, very useful for us as C programmers. The fact that the layout of C structs is deterministic makes it so that we can use this pointer syntax to reference structs, right? So that we can actually access the members of a struct without having to pass the entire thing by value. And so yeah, let's briefly talk about a really fun, depending on how you define fun, topic called field alignment. So, field alignment. What on earth is field alignment? So, field alignment is essentially the process of ensuring that all of the members of a field are aligned to memory addresses that are multiples of their sizes. So, what on earth does that mean? Well, let's talk about it. So, if we had, let's say that we're actually going to go ahead and write out our struct student here. So, struct student. There we go. There's our student, and there's a terrible curly brace. I'm usually pretty good at writing these. Okay, there we go. So, struct student. Our struct, as its first field, had a char pointer called name. All right, now, the size of our char pointer, right, the size of this pointer is 8. Our char pointer has a size of 8 bytes. If we do size of pointer, then we're going to get 8 bytes on our x86 64 Linux machine, which is the machine that we're going to assume we're working with for this part of the lesson. So yeah, so char pointer to name. And then we'll have a little table off here that contains the size of this field, and then the starting address, or the offset, rather, from the beginning of our struct. And so a char pointer has a size of 8 bytes, and it's going to start at offset 0. 8 bytes. 8 bytes. I may have accidentally said bits once or twice. I apologize for that. Yeah, 8 bytes is the size of a pointer. Yeah, an 8-bit pointer, a single byte pointer, means that we could only access 2 to the 8th. That's 2, 4, 8, 16, 32, 64, 128, 2. Yeah, 256 bytes of memory, which isn't really useful. So yeah, 8 bytes is the size of this, which lets us access like more memory than exists on the planet. Yeah, there we go. So yeah, so size of 8 bytes, offset of 0, and we're going to keep that offset at 0, and we can do that because 0 is a multiple of 8. The offset is a multiple of the size. And so now let's go ahead and talk about our ID. So int ID. Now, our ID is an int. An int on our hypothetical system has a size of 4 bytes. And so its offset needs to be a multiple of 4 in order to be properly aligned. So let's figure out how that's going to work. So the offset of this field has to be at least 8, right? It has to be at least 8 because we have to be able to fit our char pointer into memory, right? We can't overwrite part of that char pointer. So the offset has to be at least 8. And it needs to be at least 8 and be fully divisible by 4. And the good news is, well, hey, 8 is divisible by 4. And so we can just have this ID be at offset 8. And actually, what I'm going to do as we go through this, just to help clarify, is we're going to go ahead and draw our struct in memory. So we're starting at offset 0 up to offset 8. We'll say this is offset 8, is name. And then here up through offset 12, right, taking up 4 bytes, is our ID. Here is our ID. There we go. Great. So now let's move on to the next field. The next field that we're going to consider is the GPA. I'm reordering these from our initial definition that we just saw a minute ago to show us something. So yeah, our next field that we're going to consider is the GPA, and the GPA was a double. We want to make sure that your GPA has a good amount of precision. How would you like it if floating point round off lowered your GPA? I wouldn't. So yeah, our GPA has a size of 8. And now, looking at this diagram, we see... Oh, and Luscat, is that how it's stored together in one block? Yes, struct members are contiguous in memory. So they're kind of like arrays, in that a struct is a contiguous block of memory that stores all of these fields. Yeah, so yeah, it's not just scattered all over. It's all in kind of one parcel. And so now we go down and we look at this and we say, okay, so the natural place to put GPA would be at offset 12. However, we have a little bit of a problem, and that is that we need to align this field to a byte boundary that is a multiple of 8. And 12 is not a multiple of 8. So what we have to do is we have to insert some dead space in between our previous field and our GPA field so that we can align the GPA to the next byte boundary that is a multiple of 8. And so we're actually going to declare bytes 12 through 16 as dead space. There's actually nothing that lives inside this region in memory. This is just dead space. And CyberEME asks, why do we do this? And yeah, why would we do this? Let's go ahead and just write this double first before we give an explanation. Yeah, Raji, you've got the same question. Why does it have to be a multiple? And we'll explain this. So let's just go ahead and dump in our GPA. All right, so our GPA is now going to be at offset 16. It's 8 bytes long, so 16 plus 8 will span to byte 24. Here's GPA. So yeah, the question now is, why on earth do we do this? This seems kind of stupid. Like, why would you ever align data? Why would you waste space inside of a struct? And well, there are several reasons for this. The biggest one is that some platforms enforce this alignment. So some platforms will require you to align your data in order to load it from memory. The biggest example of this that I can think of is Spark, the architecture on the old kind of big systems from the company that used to be Sun Microsystems. So on Spark, which is an architecture I have had to deal with, you must align your data according to these boundaries. If you don't, then the processor will signal an error. It will signal an error that we call sig bus, indicating that an error occurred on the memory bus, the piece of hardware that coordinates memory access with your CPU. And yeah, it'll throw a sig bus and your program will terminate because the processor will say, hey, no, you can't access that memory like that. This is an issue that I have encountered while working. I was working with a piece of software that was attempting to pack data as tightly as possible. That was part of the project I was working on, was introducing data packing. And my program worked great when I ran it on our Linux boxes that were on x86. Had no issues. I was like, cool, it works. And one of my coworkers told me, okay, hey, it's great that you've got this working. Have you tested it on our AIX and Solaris boxes? And I said, oh no, our what? And so yeah, so AIX is an old operating system from IBM that runs on all kinds of different machines. We had it running on IBM mainframes. And thankfully, IBM mainframes support a degree of unaligned access. And so my program worked fine. And then I went to Solaris on the Spark machines, and I ran my program, and I almost immediately after establishing, database connections and pulling down schema and stuff, got a SIG bus. And I sent a message to my senior engineer who I talked to earlier in the day. I said, "Hey, what is this? Like, what's happening? Why am I getting first off, what is SIG bus? That's not something we have really on x86. Why am I getting this?" And he didn't actually know either. And so I had to spend part of a day reading the documentation for the Spark architecture to figure out why that SIG bus occurred, and turned out it was an alignment issue. And so what I had to do was reorder things and rearrange things and change my file format a little bit so that it would support aligned assignment on Solaris, but still pack on everything else, and that finally got it working. But it was a massive pain in the butt. So this is why, by default, C structs pack. Some architectures do not support unaligned unaligned memory accesses. The other reason why we might do this is actually that sometimes it can be faster to do aligned accesses than non-aligned accesses. And now I've written a CPU, you probably don't want to, but written a CPU in Verilog, and I'll tell you, I did one architecture that supported unaligned assignment and one that supported aligned assignment. The one that forbade unaligned assignment was faster. It was faster because of the way that we had implemented our memory. And so on some architectures, it might also be faster to do aligned assignment than unaligned. And so that is why C performs this alignment. It does it for portability, to ensure a consistent memory map between different architectures, and it does it partially for performance. So yeah, that's why we have this weird alignment thing in the first place. And so now, just as a further sample, yeah, and CyberYemi says time-space trade-off. Exactly, yeah, it is a time-space trade-off. I mean, on some architectures, it's a your program running space trade-off. But you're right, it is a time-space trade-off on other architectures, where we're saving some time by using a little bit more memory. And we can totally get away with this. Memory is super cheap. There are some old C compilers, though, that did not align. They didn't align because memory turned out to be the bottleneck for programs, not processing speed. But now we've kind of flipped that, where memory is super, super duper cheap, and we can kind of just assume that we have enough memory to do whatever we want. But we want to make our programs run faster because time is now the constrained resource. So yeah, that's why we do this. And I'm going to go ahead and add one more field to this. And I'm going to add, just to say, another int. And this is just going to be int, credit hours. We'll do our credit hours. There we go. Okay, so our credit hours, this is an integer, so it needs to be aligned on a 4-byte boundary. And so what we're going to do is I'm going to say, okay, so my credit hours now are going to be on a 4-byte boundary. My current offset is 24. 24 is a valid multiple of 4. And so I can just dump credit hours right here, occupying 4 bytes, so spanning till address 28. And so we can do this. Great. So, now let's talk about some things that we might want to do to avoid this type of thing happening. So, typically, we actually do want to save as much memory as we can, right? We don't want to kind of frivolously waste memory. We really want to try and make sure that we can arrange things as tightly as possible. And so what we are going to do is we're going to figure out if there is a way that we could fit all of these things into memory without any dead space. And there actually is. So the way that we are going to do this, and this is kind of odd, and actually it's not kind of odd, it's very odd, is we are going to arrange our members from largest to smallest. Yeah, CyberYemi in the chat, smallest to largest. Not quite. Smallest to largest is actually not a very good alignment because we're still going to have dead space, right? When we go potentially from int to double, if we have an odd number of ints, we're still going to have 4 bytes of dead space. But as a generalizable rule, if you want to tightly align your structs, you can go from largest to smallest, which is nice, right? That's actually quite the nice thing. But now there's actually something that I have failed to mention, and that is that structs themselves have to be aligned. And structs are aligned according to the size of their largest member. So, if we want to figure out how to align this struct student, we need to figure out the size of its largest member. And in this case, the size of its largest member is going to be 8, right? The largest member being either name or GPA, both of those having a size of 8. And so at the end of this struct, we're actually going to allocate another 4 bytes of dead space. And so bytes 28 through 32 of this struct are actually going to be dead space. And now, why would you do this, you say? Why on earth would you append dead space to the end of a struct? That also seems really, really, really dumb. Well, the reason we do that is because of arrays. Right? Think about it. If we have an array of students, then we need to make sure that all members of all of those structs in that array are properly aligned. And so if we were to just place another struct student right here at offset 28, what would happen is that our pointer would have to start on an offset that is not a multiple of 8. And so as a result, we add extra padding to the end of our struct in order to make sure that it can be aligned on a boundary that matches the size of its largest member. And CyberGammy says, directly access them without having to go through all that. Yeah, you could. You could just do a whole bunch of pointer math to access these. And I mean, that is actually what structs compiled down to, right? In assembly, you just see a whole bunch of offset math to do memory accesses, and you can. But, you know, we're working in C, which is a slightly higher level language than assembly, and so we would really like to kind of use these convenience features as much as we can. The question, does Java do this too? What version of the JVM, what platform? Right, so I don't believe that Java does alignment. And actually, if Java does alignment, it probably does optimizing alignment, which means that you're going to arrange your fields from largest to smallest to avoid inserting padding if at all possible. So yeah, I think Java might do that internally. I haven't actually read the source code of any JVMs, so I'm not really sure. Well, I haven't read much of the source code. I haven't read the source code for classes. Although the JVM does have an actual opcode to access class members, and so I think it's just a completely different system. It's very, very different, so I'm not really sure we can compare those very well, unfortunately. Muscat, can the compiler not do largest to smallest for us? It can. You know, hey, you're right. I mean, you could totally do that. You could just say, well, hey, compiler, why don't you arrange things the smart way? Come on, you're smarter than me, presumably. Why don't you just arrange things for me? And the reason why is that you don't always want to do that. Sometimes you actually really, really, really want things to be unaligned. And so a really good example of why you might want things to be unaligned is an old image file format called TGA or Targa. This was an image format that was used back in the days of, of DOS and early desktop publishing. It was one of the first image formats to support true color. So, where you could have your, 24 or 32-bit colors that allow you all the fancy colors that you see on the screen today. And the Targa image format requires unaligned accesses. It doesn't require unaligned accesses, but requires your fields to be in a certain order. And that order is, it has several chars at the beginning, and then several shorts, and then it goes to several ints, and then back to chars, and then shorts, and those can actually violate alignment. And so, to properly write, if you want to write fast support for the Targa image file format, you have to do something called packing your struct, and we'll talk about that. But anyway, I do want to mention one more thing while we are on the topic of struct alignment, or of field alignment. And that is arrays. So arrays are super cool. We like arrays from other programming languages. And so let's actually go ahead and, I'm just going to put an array into this struct. Let's see here. So I am going to very carefully attempt to make some space. There we go. Yay. Okay. And now what I'm going to do is I am going to insert a char array. I'm going to insert an array of 3 chars. And what this char array is going to be is, what actually should this char array be? Let's say that it's the student's initials. We might need initials for things. Sometimes we have people initial documents in addition to signing their names. And so let's say that we're going to store the student's initials. And now I'm committing a horrible faux pas that's, in line with the very classic document, programmers don't know anything about names. Or what programmers don't know about names, and that I'm assuming everyone has 3 initials, which is not true. I have 4 initials, so hey, it totally doesn't work, but we're going to go with it because it shows us something. And so now arrays are aligned based on the size of their type, so the type that they store. And so if we have an array of 3 chars, well, a char, right, is only aligned to a single byte boundary, right? Chars are 1 byte long. And so the size of this array, I'm going to write as 3 times 1. 1 being the size of our data type, which is what we have to align based on. And so it's actually very easy for us to align this new field, right? All we've got to do is I very carefully try and erase. No, we're not going to do that. Here you go. There we go. Great. And so the way that we are going to attempt to align this, there we go, there's a line, try and make these match up. Yeah, good enough. Is that I'm going to align it to a 1 byte boundary. 12 is a 1 byte boundary, and so that works. So the offset is 12. And this array is going to end at address 15. Right, because we have 3 chars. This is initials. But then we still have a single byte of dead space, right? We still have a byte of dead space between the end of this array and the next double, because the double must be aligned to an 8 byte boundary. And so we're still going to have a little bit of dead space here. So yeah, that is how structs are aligned in C. Arrays are aligned based off of the size of the type that they contain. Normal data members are aligned just based off of their sizes. And structs are aligned based off of the size of their largest member. And I'll go ahead and write that last part because it's something that trips people up a lot. So the reason that we extend this to 32 is we align to the largest member. Line by largest member. There we go. So for anyone who's reading the notes, hopefully that will make this less confusing. Line by largest member. Okay, awesome. And there we go. So that is how field alignment works in C. That's all we really need to know about field alignment. Different platforms will align in slightly different ways, right? Because the size of these data types might be different. But it is universal that field alignment will occur. And so now let's actually go back into CLion here and let's actually test this out, right? This is something that should be easy to test. I should just be able to take size of my struct. And so let's go ahead and copy that same definition that we wrote in the document. So let's see here. So we're going to have a char called initials. It's going to be, or a char array, 3 elements called initials, double for our GPA, and an int for our credit hours. And so now I'm going to go ahead and comment this stuff out because we just changed a bunch of stuff. But what I'm going to do now is I'm just going to go ahead and print the size of my struct student. So I'm going to say size of struct student. So we'll go ahead and run this now. And we see, just like we were expecting, size of student, 32 bytes. Right, so we can see here that we've got our name, our ID, our initials, our GPA, our credit hours, and then we've got those 4 bytes of dead space that the C compiler is now showing us by making the size of our struct 32. And in fact, hey, we could even check our offsets if we wanted to. We could do that. So why don't we go ahead and do that? Sure, why not? And so we're now going to use another compiler directive called offset of. And what offset of does is it takes a type and then a member variable. And so what this is going to do is it's going to say, okay, I'm going to get the offset of name at the beginning of a student. And so we expect that to be 0. ID. Initials. GPA. And credit hours. There we go. Now let's go ahead and run this. And let's confirm that what we were doing was correct. So, size of student, size of student 32. Offset of name is 0. ID is 4. Oh, right, we are on Windows. Oops, this is actually not the correct platform that I want to use for this. Let's go over to Linux. Right, because Windows alignment rules are a little bit different, and all of my students are going to be working on Linux, so we're not going to talk about Windows. We're going to talk about Linux. So let's see here. Give me 1 second to pull up a Linux terminal for us. I'd forgotten that we would need one today. My apologies. Here we go. Okay, cool. So let's do a directory listing. We've got our program. Let's go ahead and compile structs.c. Yeah, I know. I'm sorry, XISZ. Yeah, I know. Oh, right. And actually, if you want offset of, that is in another header called stddef.h, as the compiler is very nicely telling us, right? So GCC compiler warnings are actually pretty nice. It tells us not only what we did wrong, but then gives us a suggestion. It's like, hey, offset of is an stddef. Did you forget to include it? And I'm like, yes, I did, GCC. Thank you. And so now if we recompile this, there we go. And we'll go ahead and run structs. And there we go. And so now this is lining up with what we expected because, right, now we are on Linux. And so we'll see offset of name is 0, ID is 8, initials is 12, right? So there's our character array aligned to a 1-byte boundary. Our GPA at 16, and credit hours at 24. Which exactly lines up with what we had written on our notes. So now let's talk about one more thing with this, which is I mentioned that you can pack these things, so you can actually try and cram a struct into as small of a space as possible. And your compiler actually will provide some support for doing this. And so let's think about, here, I'll go ahead and switch back real quick. Let's think about what the minimum possible size of this struct is. Well, to get the minimum possible size, I'm just going to add up all of these sizes here. So that's going to be 8 plus 4 is 12, plus 3 is 15, plus 8 is 23, plus 4 is 27. So the smallest possible size of this struct, where we cut out all of the fluff, should be 27, but it's not actually going to be, because we will still have this padding at the end, and so the size of our struct is actually going to stay 32. So let me think about how I can shrink this down. Well, if we remove initials, then we should be able to shrink our struct down. So let's talk about how we pack a struct. To pack a struct, and this is honestly not something that you need to retain. It's mostly trivia, but it's kind of cool trivia. We use a directive called hash pragma pack push 1. So yeah, Unterminated, yeah, okay. So what this is doing is it's saying that I want to push onto the stack of packing directives true. So what I'm basically saying is I want to make this structure packed. The C preprocessor is really weird. It maintains lots of different kind of parameters like this as stacks. And so yeah, so we're pushing true onto the stack. And now I'm going to go ahead and pop my packing directive. And so now if we run this, you'll see something a little bit different. So especially watch this member GPA. So remember that previously, when we had compiled this program, GPA had an offset of 16 because we aligned it to an 8-byte boundary. But there was some dead space in there, right? There was some dead space between initials and GPA. So now that we are packing our struct, we see that it's a little bit different. First off, it looks like GCC actually kills the dead space at the end too when we pack. And then you can see GPA is now aligned to a byte boundary of 15 and credit hours to 23, which are very obviously not multiples of 8 and 4, but we told the compiler to pack our struct, so it will do it. Now, this looks like a good way to save memory. Don't do this unless you have a very good reason to. Don't even attempt to do this unless you have an extremely good reason to do it. Partially because, again, your program just now straight up may not run on some platforms, or your memory map may differ between platforms, because if you run this through a Solaris compiler, it's going to say, or for Spark, it'll say, well, I can't compile your packing because I can't pack, so here you go. It's just going to give us the previous struct. So yeah, BlueJ, it's not aligned now. Yeah, we told the compiler not to align our struct by using this pack pragma. And so yeah, don't do this unless you have a really good reason to. Again, like I said, if we were trying to read that file format, TGA from earlier, which is something that I've had to do before, you can pack your struct, but a much better way to save memory is simply to order our members. Right, so now we've ordered these members from largest to smallest. We've ordered them from largest being our 8-byte fields, our 4-byte fields, and our field that only requires a 1-byte alignment. And so now if we look at our struct, we'll see that, well, I don't think the size is going to change, but our offsets will definitely change. And so if we go back into our terminal and we recompile this, there you go. We'll see that the size of student is still 32 because we couldn't do any additional packing. But if I remove this field initials, and comment it out down here too, then we'll see that the size of our struct has decreased not just by 3, but by 8. And the reason it decreased by 8 is that we now, remember that we have to align our struct to an 8-byte boundary, but we're now on an 8-byte boundary, right? The end offset of this struct is 24, and so we don't have to do any additional padding. So yeah, if you really need to save some memory, I would recommend ordering your fields like this. Don't try and use Pragma Prac again, unless Pragma Pack. That is a tongue twister. Unless you have to. So yeah, that's all I'm going to say about packing. Okay, cool. So yeah, that's struct alignment. Just an interesting thing that goes on with C behind the hood. That also, now that you know how these things are packed, or are not packed, are aligned, sorry, it will allow you to compute the memory usage of your C programs. And so yeah, now just in your head, if you know the size of a struct, you're making an array of that struct, you can very quickly calculate how much memory that is going to use without even having to compile and run your program and determine the size, which is really great if you're trying to plan out a big program that's going to use a lot of memory. Speaking of memory, let's talk about one more thing today, and we're going to talk about the thing that this is probably the second most fearful topic for C programmers, but it's again one of those things that I think partially stems out of the fact that people are scared of pointers, and also that people are scared of memory leaks. So what we are going to talk about now is dynamic memory. Cyber Yemi, the first most thing people are afraid of is pointers. It's definitely pointers. I've seen so much pointer anxiety amongst beginning C programmers, it's unreal. But again, I think everyone who's been watching this series, I hope, is now like pretty comfortable with pointers after our big 2-pointer days and the frequent explanations. By the way, if you're still confused on pointers, if pointers are still scary for anyone here, then you can go back and read the notes. I publish all of the notes that we make as we go through these lessons. So yeah, I'll post in the end in the chat a PDF of all of our notes, and pointers are a prominent feature. And it explains how we read pointers, how to work with pointers, how pointers apply to arrays, and then now how pointers affect field alignment. So yeah, it's a nice, real good overview of memory management in C. And Luscat, I feel like you can quickly miss how much memory you use in Java. Oh yeah. I mean, Java memory management versus C memory management is, out of this world, right? Partially because Java pre-allocates a giant heap, so that'll, affect it. But yeah, also just because, I mean, we don't think about these types of things when we're writing Java. We're at a lower level now. We're at a level where we are now directly interacting with features of the CPU, right? Aligned access. And where potentially every byte can count if we're writing code for a constrained machine, like an embedded system. So yeah, it's a really nice thing that C allows us to do. We know just right offhand how much memory we're using. It's a really nice property. But yeah, let's talk about dynamic memory. And Sabriemi, you predicted the future. Yes, indeed, you did. You did predict the future. We're gonna talk about dynamic memory now. Mess with logic gates. Maybe. We could. That's always a fun topic. But yeah, for now we're going to stick with C, and we're going to talk about dynamic memory. So, let's talk about memory, just as a whole. So far, we have encountered 2 types of memory as we have been writing programs. We have worked with a memory region called the stack. The stack being where our local variables are stored, right, on the call stack, like we mentioned, a little bit ago. Right, so when we make local variables, they're allocated in a stack frame on the call stack, and we manipulate them on the stack. We also have something called static storage, which essentially means that when your program launches, a particular variable is going to be given a fixed memory location, and it's never going to change from that. So it's a fixed memory location pre-allocated. When your program starts, you know that, whatever structure it is always going to live there. And we indicate those types of variables using the static keyword. And so, if I wanted to say, static const char pointer student name equals test student, then what this word static here says is that we're going to, when the program starts, allocate a region of memory to store this string, copy this string to that region of memory, and this address is not going to change for the runtime of our program. It's going to be static. It's going to live in one place. Static also means some other stuff, and we will talk about that, but we're not going to do that for now. But yeah, so that's what static means. Then dynamic memory is what in Java you probably heard referred to as the heap. The dynamic memory is where we perform allocations of data structures for which we do not know the size. Prince logic, it's the same as Java for the static keyword. Yeah, kinda. Yeah, it's in a fixed memory location. You can mutate it from anywhere. Static also does mean a slightly different thing in C. It also means that that variable is confined to the current translation unit. And when we talk about how C compilers read your program, we'll talk a little bit about that, just a little tiny bit. But yeah, so it also means something else. It also means something kind of like private in Java. But yeah, for now, we'll just consider it to mean has a fixed memory location. And then, now we've also got dynamic memory, which is the heap, right? So this is where we allocate things that we don't know what their size is going to be ahead of time. We had a question asked earlier in the chat. So out of curiosity, in C, can you instantiate an array with a size that isn't predetermined? So, could I say, int sum size equals 24, and then say char, array sum size. Some compilers will actually let me do this, and it's a cool thing. But some won't, and more specifically, if I had a function that was trying to make this array, you know, I was trying to return a char array. We'll just make it void. There we go. We're going to pass it a size. Then something interesting might happen on some compilers. It seems like GCC is actually okay with this, and I think that's because it's doing some magic kind of behind the gate. But sometimes you cannot actually allocate. With some compilers, you cannot allocate an array of a size that is not predetermined, and so we would have to do that on the heap. And let's get, you remember from C++, a star can later be an array, so is the star name not in dynamic memory? Well, I mean, we can have a pointer to anything, right? We can have a pointer to things on the stack. That's actually all the pointers we've made so far have been pointers that were to things that were on the stack. And so, yeah, we can have pointers to things that aren't in dynamic memory. Totally. And CyberYemi has told us how we're going to work with dynamic memory. So now, let's say that instead of, apologies, putting this student on the stack like we did previously, so let's go ahead and instantiate another student. This is initializing this student on the stack. And sometimes we do want to stack initialize something. But now let's say that I want to return this student from a function. So let's say that I'm going to write a constructor called makeStudent. And all it's going to do is take a name and an ID. And we'll start off this student with a 0 GPA and no credit hours. So what I can do is I can say, okay, I'm going to just go ahead and return this student. And there you go. And that's how we would make the student and just return it. But sometimes we may have a struct that's really, really big, or that has an indeterminate size of a parameter. So let's say, what about this student's initials? Right? What about their initials? I'm going to make this a pointer now. And we don't actually know what the student's initials are ahead of time. And so I may say, you know, int num initials. And now I have no way to actually make an array for the student's initials. I can't. This is a size that is not predetermined. And so I just can't say, you know, new array, blah, blah, blah. I have to think, well, how on earth am I going to allocate these initials? And so here's what we're going to do. I'm first off going to reformat my code so it's easier to read. And CyberYemi, we don't know the size of name, and that's true, but because we're having the user pass us that pointer, we assume that they have handled the memory allocation in advance. So yeah, we don't need to know the size of name. It's just a pointer that we're storing. And initials is also going to be a pointer. But now, so what I am going to do is I'm going to assign to my initials the return value of this function. So this function right here is about to become either your best friend or your worst memory. This is malloc, stands for memory allocate. It is the function that we use to allocate memory on the heap in C. And what malloc does is we pass it a size. So we pass it the number of bytes that we want to allocate. In this case, since this is an array of characters, we say we want to allocate the number of initials times the size of a character. And so now we've got an array with this size, right, with this number of bytes allocated in dynamic memory on the heap. We didn't know the size in advance, but hey, it's not a problem. We can use malloc to dynamically allocate this structure. And so now, after we run this function makeStudent, so let's say struct student makeStudent. Oh, not makeStudent, sorry. I'll call it testStudent. Goes makeStudent, their name, test student. If I can type ID 1, 2, 3, 4, 5, and we'll give them 3 initials. And now we can actually, now that we've got this array, we can do things with it. We can copy values into it. And so if I wanted to make the student's first initial A, then all I'd have to do is say test student dot initials at 0 equals A. Or in this case, their name is test student. So I'm going to make their initials T and S. And we'll go ahead and make the size of this array 2. And here you go. Now we've got our student with an initials array allocated in dynamic memory that we can assign values to. Cyber Yummy, if you wanted to be able to access the third letter of a student's name, would you have to do this? Oh yeah, you could do this. Yeah, if you wanted to get the third, the third letter of name, then you could just say test student dot name at 3. And yeah, well, I guess it'd be 2, right? The third letter. And yeah, that's how you would do that, right? We assume that this string here, test student, has a memory address already. And string literals in C are allocated in something called the constant pool, which is in static memory. And so yeah, so this string is actually in static memory. So yeah, we can just access it like we would a normal array, right? It's just a pointer. It's a pointer to the location in static memory at which this string has been allocated for us by the compiler. So yeah, so we can totally access the name like this, but we'll stick with the dynamic memory for now. And Raven CCTV asks a good question, which is, isn't it good practice to cast the result from malloc? And you can. So malloc returns a void pointer. And something that a lot of C programmers will do, C programmers are typically very, very, very proactive about casting, and it's because C's type system is so weak. So what a lot of C programmers will do is they'll say, well, this is supposed to return a char pointer, so here, give me a char pointer. And we can do that, right? We can totally allocate a char pointer. Or we can allocate, we can allocate our char array and cast it to a char pointer that is the expected type. Why you would do this, I've never heard someone give me a very convincing explanation. Maybe you can give me one. But yeah, typically C programmers are just very proactive about casting. So you'll often see people cast the result of malloc since it returns a void pointer. And now something that I will note about malloc, and this is something that hopefully you never encounter because you write good programs, is that malloc by default will return the memory address in dynamic memory where that memory that you requested was allocated. But it doesn't have to. If that memory could not be allocated, so let's say you ran out of memory to allocate, or your program exceeded its memory allotment, the maximum amount of memory you allowed that program, malloc will return null. And so what a lot of people will do is every time they call malloc, they will then check the result. So they'll say, if, they'll assign the pointer and then say, if this equals null, then they'll throw some error. And we could actually do that. I mean, we could include this file called assert.h, which contains one macro that all it does is it determines the truthiness of an expression. So I could just say assert testStudent.initials is not equal to null. And if testStudent.initials is equal to null, then this will throw an error. Which is really nice. It'll halt the program and throw an assertion failure. And so the compiler knows the length of the string and stores it. If so, if you change the name, would you have to garbage collect the previous name? No, you would not. So again, string literals in C are statically allocated. So you can't really, you can't deallocate static memory. It's not permissible to deallocate static memory. But what you could do is you could reassign the name. Yeah, so if you wanted to overwrite this variable, testStudent, overwrite the string, testStudent, you could do that. So you could say, if you said, student.name at 2 equals v, then this string would become tevstudent everywhere, because it would have changed in static memory. But yeah, if you actually want to change the name itself, then you would need to assign a different pointer, meaning that you would either need to assign a new string constant, which you can do. Again, this is going to allocate a string in the constant pool. Or you could allocate the memory dynamically, allocate it on the heap. And so this works really great. I can run this program, and we've got no problem. Right? No problem whatsoever. Yeah, you're confused because strings are char arrays. Well, right. So a string is a character array. So what the compiler does when it sees these string literals is it says, hey, I have a constant string. What I'm going to do is I'm going to cache that constant string. Oh, we've got some spam in the chat. Let me get rid of them. Yeah, they're gone. I'll ban them later. So anyway, no one click on that link. So anyway, so now that the compiler has seen this constant, it says, hey, I need to put this array somewhere in memory. And I know that you've used this literal, and you probably want this literal to persist past the scope of the current function, right? If you don't want to assign a string and then have another function call later accidentally overwrite that string because you were trying to store a pointer to something on the stack. We don't want to do that. And so what the compiler does, it says, you know what, I'm going to assume that you want to allocate this string in static memory. You want to allocate it so that it has a fixed memory address that will just stay there for the runtime of the program. And so strings are character arrays, but they're character arrays that are allocated in static memory. Hopefully that makes a little bit more sense. So yeah, so we just keep them in a static memory location so that you can reference them from anywhere in your file, and you don't run the risk of accidentally overwriting them with function calls. Okay, great, good. Glad that clarifies it. So believe it or not, we can just run this program now. This will work. So we can just run this, and we see that we are allocating dynamic memory, and we're good. And this works awesome for one student. But now let's say that I want to make 7,000 students, right? So I want to make 7,000 students. And actually, I'm going to make more students than that, but yeah, you know what? We'll just stick with 7,000 for now. And hey, that actually finished pretty quickly too. Let's allocate 7 million students. Oh, right, and C doesn't allow you to use these fancy little separators, but that's fine. And that also completed pretty quickly. Interesting. Okay, let's increase the number even more. Wait, 7 million times 24. Okay, yeah, let's increase this a little bit more. 700 million. And this has taken a while. 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 Let's actually see what's happening here. So let's open up Task Manager real fast, and let's see how much memory this is using. Let's see here. Oh, that's interesting. Assertion failed. Test student.initials is non-null. Ooh, something happened. Okay. You know what? Let's run it again. Let's run it again. Let's see what happens as we run this program. And more specifically, what I'm going to do is I'm just going to jump over to this tab right here called memory and look at the memory usage on my system. So let's run the program. And let's watch the memory usage. Oh, you see that? It might be a little bit hard to see because of the scale of the stream, but you can see that our memory usage is just climbing and climbing, and all of a sudden, it stops. And now, why did that happen? Well, it tells us that initials was null. So malloc returned null. And so what happened is we exceeded the amount of memory that is allowed for our program. We ran out of heap space. Yeah, exactly. This is equivalent to a Java out of memory error. We ran out of heap space. We can't allocate anything else. And so the operating system said, hey, you're using too much memory. Go. You're done. You're done. And the operating system, the operating system didn't kill our program, but it had malloc return null, which means, hey, you can't access any more memory. Allocate any more heap memory, rather. So yeah, this becomes a problem. We have what is called a memory leak. We have a memory leak. A memory leak is what happens when we allocate dynamic memory and we forget to free it. So malloc it's just going to keep going. It's just going to keep going. It's going to keep allocating memory until we can't anymore. And because C does not have a garbage collector, that memory is never going to be deallocated, right? We have to explicitly tell the runtime that we want to deallocate this memory. And the way that we do that is by calling a function called free. So if I want to free the dynamic memory that was used by student initials, or by test student.initials, I'll call this function free on test student.initials. And what this does is free says, hey, I requested this memory from you, operating system. So I requested this memory, I used this memory, and now I'm done with this memory. So you can actually use this memory for something else. If I try and allocate something again in the future, just remember that, hey, I gave this memory back. I was good. I gave this memory back. Why don't you, maybe make that region of memory open for me again in the future so I can access it again? And that's what's happening here. And so we're freeing this memory, meaning we are just releasing it back and telling the memory allocator, hey, I'm done with it. You can reuse it. And so now, if we go back and we run our program again, although actually I don't want to switch yet, let's open Task Manager back up and watch our memory usage. So let's go to our Performance tab here. Go ahead and run our program. So this is the program with free. And watch and see what happens. You'll see that the memory usage stays constant. And why is that? Well, it's because, yeah, we are allocating memory, right? We are allocating memory for this initials array, but then we're releasing it at the end. And so as a result, we're not going to run out of heap space like we might have prior. And so that is why it is incredibly, incredibly, incredibly important that every time you allocate memory in a C program, once you are done with that memory, you free it. You have to free it. And now, yeah, Cyber asks, why would you want to free it immediately? And you're right, this is kind of a stupid example, right, of where we're just allocating the memory, checking it, and then freeing it. It's really just an example to show you how memory allocation works. But yeah, you might want to use this struct for some stuff and have it run around in different parts of your program. And then finally, once you're done with that struct, maybe after you've done a bunch of things with it, then you can deallocate the memory. And so yeah, you can, it's totally fine to just kind of, yeah, you can keep dynamic memory live as long as you need to. It's just important to remember that once you're done with it, you should free it. And so yeah, this leads to a really common situation when we forget to free called a memory leak. It happens almost constantly when we write C programs. And actually, there's something that I saw just the other day that I thought was really, really funny that I think you'll now understand now. And that is, let's see here. Let's see if I can get this pulled up. Yeah, so this is a tweet that I saw about dynamic memory. Yeah, this is a video. Let's see here. We'll go ahead and... Oh, no. No. I didn't want a full screen it. I just wanted it to be bigger. Can I not do that? No, Twitter's going to keep it the same size. Well, hopefully you can see this. But anyway, yeah, so here's a brief meme about dynamic memory. And we'll go ahead and pause our music here. Anyway. So yeah, maybe I have a crappy sense of humor, but I thought that was just hilarious. Yeah, that's one of the funnier things that I've seen for a while. So yeah, but you can actually see, it shows you, how a memory leak happens, right? You keep calling malloc, you call malloc repeatedly, you don't care about actually freeing the memory, and eventually you run out of memory. And your memory usage just continues to skyrocket. And now, it is a little bit inaccurate in that if you forget to free memory, you won't get a blue screen of death. Maybe if you do it in a driver, you will. But, if this program runs out of memory, as we saw, malloc just returns false, or it returns null, right? So it's not the end of the world. But it is important to remember that, we should always free memory after we allocate it. And so, Prince Logic, how do you know how much space you're allowed? It's a good question. Your operating system will automatically allocate you a certain amount of space, and you can change that. So, for example, this is a debug build of this program, which means that we actually aren't allowed as much memory as we otherwise might. Be. If I compile this in release mode, oh geez, I don't know how to do that. I don't know how to do that on Visual Studio. With the Visual Studio compiler, no clue. But if we compile this in release mode, then you'd actually see that we probably get more memory, and part of the reason for that is that in debug builds, we get less heap space so that we can catch memory leaks like this. And is it the same every time? It'll be roughly the same. There may be some additional factors that can affect how much space you're allocated, but it'll be roughly the same every time. But you can't actually change it when you run your program. On Linux, there's a command that allows you to change the amount of memory, like the maximum memory allocation of your program. It also lets you change the size of the stack, and so if you have really deep recursion, you can just change the stack size when you launch your program to make sure that you don't get a stack overflow. Or what the GCC compiler calls stack smashing, using the coolest possible name. But yeah, so there are ways around this. But thankfully, the debug build's memory allotment is pretty low, which allowed us to catch this memory leak in real time. So now, what we would like to do is demonstrate a few more memory allocation functions in C. So let's say that I actually want to print these initials. So I'm going to say printf initials, and it's going to be a string, and I'm going to print teststudent.initials. Lovely. And can I spell? No, I can't. And I'm going to lower this down to like 5. There we go, so that we don't spend all day watching this run. All right, so let's go ahead and print the initials, and let's see what we've got. That's not really what we wanted. And actually, let's comment out this free real quick just to show us something. Yeah, so about this. What's happening here? Well, you'll remember that in C, when we allocated memory on the stack, it wasn't 0 initialized by default. We had to initialize it ourselves. The same thing applies for dynamic memory. So yeah, if you want to allocate dynamic memory, it is going to be uninitialized, meaning that the value that is going to stay there in dynamic memory, or the value you get in dynamic memory, is probably just going to be some junk left over from a previous allocation. And Cyber says it looks like wingdings. It kind of does. Blue Jay says moon runes. Yeah, it's actually, I think it's code page 437, or like ANSI character encoding printout, but I'm not really sure. I think that's what Windows default printf does. And moon runes, no, that's a programming language called APL. This isn't nearing that level yet. Anyway, so what happened is we forgot something that's very, very crucial in C, which is we forgot to initialize our memory. And so I will fully admit that a string is not the best example of a way to do this, but it's easy. So if we want to allocate memory by default to 0, so if we want to 0 allocate this memory, then instead of calling malloc, we call a function called calloc, which actually takes some slightly different parameters. It's going to take, as a parameter, the number of elements to initialize and the size of each element. And so calloc, it's going to take the number of elements to initialize and then the size of each element, and it's going to, by default, 0 out all of the elements in the array. And so now if we run this, then we should see that all of our initials should be empty, right? Because they were initialized to 0, which means that the first value in the string is going to be a null terminator. And that is indeed what we get. We get no output because we zeroed out our strings and we immediately hit a null terminator. So yeah, that's kind of nice, right? So now we've got a function to 0 allocate. So you might ask me, well, wait a second, why would I use malloc then? Like, why would I ever use malloc? I can just use calloc and have things 0 initialized. Well, you don't always want to 0 initialize, right? You don't always want to zero initialize things. If you're going to immediately put values into that memory, why would you zero initialize it, right? There's no need to do that. All you're doing with the zero initialization really is wasting time, right? You're just wasting CPU time in that you have to loop through all that memory and set it to 0, when instead you could just place the values in there that you know you're going to be putting in there, right? So don't always call calloc. Actually think about the situation and determine whether or not you really need calloc, or whether you can just use malloc and assign the values yourself. Most of the time, you're going to be assigning the values by yourself. And now calloc, like malloc, allocates in dynamic memory, and so we have to call free afterwards. And now we've got one more function that we want to talk about to allocate memory, and that is probably an even weirder one called realloc. So, realloc. So let's talk about realloc. What realloc does is it's a lot like malloc. So actually, we can't really use realloc here. We're going to switch this back to malloc real quick. We will use realloc down here. So now what I'm going to do is I'm going to say realloc test student.initials. And I'm going to, let's say I'm going to bump it up. Let's say that the student actually has 4 initials. Okay, so what realloc is going to do is as follows. It is going to first attempt to grow the memory region that begins at this pointer. So it's just going to try and grow that memory region. It's going to say, hey, hey, memory allocator, are there 2 extra bytes? Are there 2 extra bytes after the end of the initials that I allocated previously that you could give me? And one of 2 things may happen. The memory allocator may come back and say, yeah, absolutely, I do have 2 more bytes. Here you go. And realloc will return the same pointer. It'll return the same pointer because the memory address at which testStudent.initials lives did not change. However, sometimes we may try and reallocate, and there may not be enough space in memory at the same location to allocate that new block of data, right? Because remember, when we call malloc, realloc, calloc, those regions of memory that are returned in the heap have to be contiguous. And so if we cannot grow the region of memory pointed to by that pointer to the size that we requested, then realloc will allocate a new region of memory, copy over all the data from the previous one, and then free the previous region of memory, and return to you the new pointer that was allocated. And so, when we call realloc, we have to remember that sometimes it will grow this pointer, and this pointer won't change. But we have no guarantee of that. And so what we need to do is if we ever call realloc, we need to make sure that we reassign that variable. Right? In the growth case, all that's going to happen is that variable is going to be reinitialized to the same thing. There's no harm in doing that. But if we have to move this region of memory and copy the values in this region of memory, we run into a problem, right? We run into the problem of the fact that our pointer will change, and we didn't pay attention to that. So at that point, initials would be pointing to an invalid region of memory, and we would end up getting a segmentation fault because we would attempt to deallocate memory that is not ours. Or, we might not get a seg fault, but we would have a little bit of an issue. We might allocate junk, or we might access junk memory. CyberYummy, things would be overlapping. Well, so the allocator does a really good job of making sure that nothing overlaps. But yeah, if you just keep that old pointer around after you reallocate, yeah, that pointer could totally be pointing to just some other stuff, right? That could be a region of memory that's now being used by something else in your program, and so you might just access junk data. So yeah, things aren't going to overlap, but you might be pointing to a region of memory that no longer accurately reflects what you want it to, right? It's no longer pointing to where that data lives in memory. And just like malloc, realloc may return null. And so we usually want to check the return value of realloc. And now you'll run this and you'll see that it doesn't work. And we're like, oh, crap, what happened? Well, realloc, remember, does not zero memory. And so, again, usually because, again, we use it to grow existing values, right? And so if I were to actually assign the values in test_student.initials here, let's say 0 equals t, and 1 equals s, we'll print the original initials, and then reallocate and reset, then you'll see that it actually copies over the memory, right? It does copy over the values that we were expecting. And then there's some garbage at the end, right? But it does actually copy our values. And actually, let me fix this just so that it's easier to see. So let's say we're actually going to reallocate initials to 10, and I'm going to just dump a null terminator at the end of initials. There we go. So now if we run this, we'll see that at the beginning, initials was TS. At the end, initials was TS. Right? And so realloc copied the memory regardless of whether the pointer changed or it stayed the same. So yeah, that's how realloc is really useful. It can be used to grow regions of memory, but it can return null, so we've just got to be careful. And now these functions can sometimes be a little bit confusing, and you may sometimes kind of forget how these functions work. And honestly, that's understandable. They can be kind of complicated. And so if you ever forget how any of these functions work, then you can do one of two things. You can use the manual pages to look up the standard library, right? So all of these functions actually live in the header stdlib.h. That's where they're defined. They're defined in stdlib. And so if you want some help on stdlib, and this is a repeat of yesterday, but I really want to make sure people know how to use the man pages, then we can type man stdlib. And this one gives me the OCaml standard library, but if you're on a Unix system that does not have that installed, or you know the, let me look it up, give me one sec. What is it? It's 3, right? So this should be man stdlib 3. Oh, it's 3.0? Really? What? Whatever. We're not going to belabor this. Yeah, section numbers. How do you pass a section number? Oh, really? Okay, stdlib.3. Okay, still give me OCaml. But if you're on a system that, this is the perils of live coding. If you're on a system that does not have OCaml installed, it'll pull up the C standard library. But if you want help, right, and we did that yesterday with string. So we typed man string, and we got help on string.h. But if you're just curious about one function, you're like, hey, I am trying to use calloc. I don't really know how that works anymore. I don't remember what order the arguments come in. And then we can just type man calloc. And, well, we get the documentation for malloc. But within the documentation for malloc is the documentation for calloc. And if we search for calloc, then we can skip here and we see there's a whole paragraph written about it. It's very nice. It says calloc allocates a region of memory for an array of n mem elements of size bytes, blah, 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 et cetera, et cetera. Right? So yeah, so it's kind of nice. We get all of this built-in help from our Unix system using the manual pages. If you're on Linux, you should have access to these. If you're on Mac OS, you should have access to these. If you're on Windows, you're screwed. Windows doesn't have man pages, and Windows actually doesn't even have a very good help system. So if you want help with all of these and you're on Windows, you'll have to look up the Microsoft documentation, which is not fun, but you can. Another brief thing about this is that if you are, and yeah, Rick Ghosh in the chat says just SSH into lab computers. Yeah, if you're at a university, you probably have a Unix lab. Like if you're in a CS or EE department at a university, you have a Unix lab. Just use that, honestly. Programming in C on Unix is just nicer than on Windows. Christ and Bill Gates. Well, yeah. Windows and C have an interesting relationship. The Windows C API is a disgusting monstrosity. But anyway, if you're on Linux and you like using Vim, like I do, right? I use Vim. My key bindings in IntelliJ are set to Vim key bindings. I use the same key bindings for Emacs, my primary editor. I use Vim key bindings everywhere. But anyway, if you are, let's say that you're just writing a C program and you write calloc, and then you're like, Vim is a text editor, Cyber. It's a text editor. It's a text mode text editor. And if you want to know how to get documentation for one of these functions, then just type Shift-K, and it'll pull up the man page. So yeah, it'll pull up the man page. That's for anyone who uses Vim who doesn't know what Shift-K does, or if you kept accidentally hitting stuff, or you accidentally hit it when you meant to type K to go up, and you were like, what happened? Yeah, that's what capital K does. It looks things up in a man page. Really useful when we're writing C and you forget how a function works. It's one key away to figure out what a function does with really good documentation. Right? Super duper useful. That's why Unix makes a really good IDE. And we've got another question. BlueJay, would you encounter these issues with WSL? No, WSL is just Linux running in a VM on Windows. This is actually, this is a WSL instance that I've got running right now, as you can see by the, like, weird path. Yeah, so it works on WSL. WSL is just whatever Linux distro you have running in a VM. Like, this is Ubuntu. At least I think it's Ubuntu, right? Yeah, it looks like Ubuntu, I guess. I don't know. But yeah, so you have access to all this stuff. And I highly encourage you that if you are writing C, you just get used to the Unix operating environment, and especially get used to using the man pages. They are probably the best documentation that we have on the C language. They're super useful, written by people who are very knowledgeable, very practiced C programmers. And so yeah, make use of the man pages. You've got them for your benefit. So yeah, just go ahead and use them. And all right, that is actually where we're going to cut it today. This was a fairly interesting day. We learned about how structs work. You learned about alignment, which is really a more interesting topic than it initially seems like it might be. It seems like it might be something that's kind of boring, but no, there's actually a lot of complexity to it. And it's pretty cool to know that if you're a C programmer and you know how alignment works, you can compute how much memory your program is going to use. Like, it's really cool. Prince Logic says Linux was written in C, wasn't it? Oh yeah, Linux is written in straight C. And if you want an example of a really big C code base, go look at Linux. If you want an example of a good C code base, look at BSD. Linux does some interesting things with the C language, and so yeah. I wouldn't recommend it as a didactic we're learning C example, but if you're in an operating systems course and you want to see how like the big guys do it, then yeah, you can totally go look at the Linux kernel source, and it's a leviathan of C code. It's kind of interesting. Now, so there we go. We also learned about dynamic memory. Dynamic memory is cool. It lets us allocate things that we don't know the size of by default. I will note that dynamic memory is also really, really useful when we're trying to allocate arrays, right? So if I want to make an array of students, then what I can do is I can just call malloc, and I'm going to pass it however many students I want. So let's say that my university has 30,000 students. And I'm going to allocate 30,000 times the size of struct student. And without blinking, my C compiler has no issue with that. And, we can assign things to this. So I can say, student R at 0 dot name equals test student. Oops, sorry about the noise. And I can go ahead and print it. And there we go. And that will give me the name of that student. BlueJay asks, when we're creating new student structs in the for loop, doesn't it overwrite the memory allocation of the previous struct of the same name? Yes, it did. Yeah, it did. When we had that for loop a second ago, undo. There we go. Yeah, so when we had this loop, yeah, this student was being allocated on the stack. And so, yeah, you're right in that every time we went through this loop, we were overwriting this student. And that is why it was very, very important that we freed the memory inside the loop. Because if we forgot to free the memory in the loop, we would have overridden that pointer and we wouldn't know where that memory was to free. And so at that point, we would have an uncontrollable memory leak that we couldn't recover from. So yeah, it's really, really important to make sure that, yeah, we are paying attention to our memory lifetimes and also remembering what happens when we allocate things on the stack, right? They may get overridden in future function calls or iterations of a loop. Why couldn't you do it outside the loop? Right. So let's step through this code. So what we're going to do here is we're going to allocate a student on the stack, right? We're going to allocate something that's the size of struct student on the stack. And the value of that struct student is going to be the value that's returned from this function, make student. And within this function, we set the initials of this student to be the return value of malloc. In other words, we set it to a pointer to dynamic memory. Then we did some stuff, blah, 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 blah. And then what happened is we said, okay, I'm going to free the initials of my student. And let's say we don't do that. So I'm actually going to just delete all of this stuff. And what I want to do is I'm just going to print the address of my student. Address of test student. Let's say we don't free this. So you can see the address of my student is the same on every iteration of the loop. And the reason for that is that C stack frames are deterministically allocated. So just like you could compute the size of a struct in C, you can also compute the size of a stack frame. A stack frame is basically just a struct, or at least the local variables in a stack frame, is just a struct that contains all of the local variables that we have declared. And so as a result, this test student is being placed in the same memory address on every iteration of the loop because we are overriding the same place in memory. However, if we are allocating the initials in dynamic memory, which is what we're doing, then you'll see that every time we call malloc, without calling free, we get a different memory address. And that memory address, as you can see, is not possible to predict, right? We can't predict how this memory address is changing. It's going all over the place. And so as a result, if we forget to free our memory here, then we're not going to be able to go back to a previous iteration of the loop and free that memory because that pointer got overridden in the next iteration of the loop. So yeah, that's why we need to make sure that we're freeing our memory. In this case, if we're ever making pointers inside a loop that we want to free, if we're ever allocating dynamic memory inside a loop that we want to free later, we've got to make sure that we do it while this variable, right, while the struct is still live. Because if we wait, we're never going to be able to get that pointer back. So yeah, so it's just really important to make sure that we are always matching our mallocs with our frees, and that we are paying attention to the lifetimes of these structs and when they may potentially go away and get overridden. The initials are in a random place. Yeah, exactly, right. Yeah, the student is deterministically allocated. It's allocated on main stack frame. But initials is in dynamic memory. And so initials is not in a stack frame. Initials, or at least the memory region pointed to by initials, is wherever the memory allocator decided to put it. And again, we can't predict that, right? I mean, you could potentially know some details about how your memory allocator works, but even then, subsequent initializations may change where things will go. And so we have no good way to predict that. So yeah, we don't know where initials is going to point to. And so yeah, we've got to make sure we free it while that value is still live. And so yeah, if we forget to free it, then we've just got a whole bunch of little tiny memory regions all over the place lying around that we have no way to free now. Does that clarify things? Great, that helped a lot to see the addresses. Good, yeah. And if at any point y'all are writing C programs and you just kind of want to go, you know, what is the address of this? It can be helpful when you're debugging pointer code, or code that uses pointers to know what the addresses of things are. You can just use the format code %p, which says print a pointer, and pass it a pointer, and you'll see the memory address. It's pretty useful, right? We've got a special printf code just for pointers. So yeah, so you can use that if you're ever curious about where a value lives in memory. All right, so yeah, that's going to be pretty much the end. Yeah, that's going to be the end of today. I'm going to stick around for just a few more minutes to take any questions that y'all have. You can just type them in the chat, and I'm happy to answer about today's lecture or a past day's lecture or just C in general. And while you get your questions ready, I am going to upload the notes from today to the cloud so that you all can access them, and I will post a link in the chat. So if you want the notes, just hang tight for a minute, and I will give you all a link. But yeah, and I'll be monitoring the chat for questions as well. So yeah, let's see here. Let's see here. Export. That looks good. Export. Let's see here. The iPad's not up, right? No, it's not. Okay, good. Good. Don't need everyone knowing everything about my system configuration. Let's see here. This is day 4. Going to go ahead and upload that. All right, great. Great. Okay, so yeah. Any questions? Prince Logic, you should upload a zip file with all the C files you've been doing at the end. Yeah, I mean, that would be something that we could do. The problem is that, as you've seen, we don't just keep these files constant, right? We often change things in them. And so kind of the end state, the end state of this kind of file never reflects everything that we did, but I could upload. Yeah, I could upload all of the files we've been working with and go through and like comment things to kind of help make it make a little more sense. I need to do some code cleanup. But that might be something that I can do on a future day. And Cyber, you've just been coding and commenting out things we take out. Oh yeah, you can totally do that too. Yeah, and I'm glad that, some people are coding along. That's a great way to learn with us as we go through this. Yeah, feel free to, have an editor window and type along with me. I'm more than happy if y'all do that. It also means that y'all can catch potential syntax errors I might make, which is good. Okay, Rick, you were reading the man page for Stircat, and it said that if dest char had less space allocated than the combined length of source and dest, unexpected behavior happens. Oh, right. Yeah. Right. So it doesn't mean that dest necessarily means to be dynamically allocated. It just means that there needs to be enough space after the end of the current destination string to fit the source string as well. And so, yeah, it could mean that you just have a statically allocated or stack allocated char array that is big enough to hold all of the data. That would be fine. You could do that. So it doesn't have to be dynamically allocated, but you're right in that if you don't have enough space to run Stircat, then yeah, you're gonna run into problems. You're gonna run into some fairly substantial problems. And we're actually going to talk about string.h a little bit more tomorrow, because we're going to use some more functions in it. Because it turns out that string.h is used not just for strings, but actually contains functions for working with any contiguous memory regions. So yeah, we're going to talk more about string.h. But that's a really good question. So yeah, we don't know what will happen. You might get a seg fault if the string is too big. You might accidentally overwrite some other data in your program that's allocated nearby. We really don't know what could happen. So yeah, it's undefined behavior in that we don't know the details of the runtime, and so it's runtime dependent, what will actually happen. But a good synopsis of what will happen if there's not enough space to do the concatenation is something bad, something you didn't intend to happen. And so, yeah, always make sure when you call Stircat you've got enough space for both strings. XISZ, in C in general, you've run into an issue throughout your course that F flush is not as good as other options. which I'm told is like int c, while c equals get char, not equal to eof, and c is not equal to \in. You still don't understand why. Oh, right. Yes. Okay. So your question has to do with buffering, and we're actually going to talk about file I/O in a little bit. It's going to be in a few days. We're not quite at that point yet, but we will talk about file I/O. And so what happens is file I/O on most systems is what we call buffered, which means that you're not actually just reading a single byte at a time, because that turns out to be pretty heinously inefficient. Right? You don't want to just call, you don't want to access a certain byte at a time, because if you're on a hard disk, then what that means is over and over, every time you call it, your disk is going to have to spin into position. You're going to have to read, if you're reading a single byte, it'll return that data to the CPU, and that whole data transfer process takes a fairly substantial amount of time. Disks are slow, it has to rotate into space, and so that takes a large amount of time. Even if you're on an SSD, access is much slower than it is to RAM, and so again, doing disk accesses is costly. It's the slowest form of memory that we have. And so as a result, your OS, it's for reading input. Oh, right, this isn't, get char, not get char. Oh, sorry. Sorry, I've misread. Sorry, I might flush SCDN. Well, I'm going to stick with the buffering explanation, actually, because I think it does have to do with buffering. And so what happens is all streams are buffered by your OS. Buffering happens for disks so that we can read a bunch of data all at once and then return it byte by byte from memory, which is faster than doing it from disk. Standard input, standard output, our input and output streams are also buffered. And you actually see that if you've ever tried to just print a single character at a time to the console without a new line, you'll notice that it doesn't actually show up. So if I go back into our program here and I just try and like printf hi without a new line, does Windows flush by default? Windows does flush by default. But on some platforms that don't flush, I guess they all actually flush SCD and SCD out by default. Let's see here, but yeah, and so if I were to, print hi, and then do some really costly operation that took a number of seconds, that hi would not show up till the program was finished when your runtime cleared SCDN and SCD out. And so, yeah, that's buffering. It's saving up output until it reaches a certain character, which for standard in and standard out is a new line. That indicates that we should flush all of the data that's stored up in that buffer for that stream to the output device, be that a disk or a console or whatever it may be. And so, let's see here. And so, yeah, so calling fflush stdin, I suppose would be you attempting to... Right, yeah, so that would be you attempting to get the single character that was input on every iteration. And that can work. But I think that, and, I haven't used get char or any of that. I don't do a lot of console input in C. I mainly am a library author for C, but, I do some of this. I'm pretty sure what's happening is that you are, when you call get char, fetching things from stdn, but you aren't allowing that buffering to occur, and that can actually be kind of inefficient. So I think it boils down ultimately to efficiency. I don't know if the behavior would change. But yeah, in general, you should only flush streams when you need to make sure that data shows up. And so for printf here, right, I'm printing hi, and if I wanted that hi to show up immediately before the OS or the runtime cleared or flushed standard in to standard out, then I could do fflush standard out to make sure that that message showed up immediately. But yeah, I'm not really sure why you would flush stdn. And so yeah, I think that the way that I guess has been told for you to do it, where you're going to call get char and then check for EOF and new line on every iteration, yeah, that seems like a better approach, because it's making sure that Yeah, I guess you're waiting until someone hits enter. Or control D, which is the end of file signifier. Yeah, okay. Yeah, so yeah, I'm not 100% sure. I don't do a lot of console input in C, but that's what I would hypothesize as to why, is that they want to make sure that you're waiting for a new line and they want you to do it efficiently. But okay, oh, yeah, I need to actually post the link in chat. So let me go ahead and go grab a link. If anyone has any further questions, or if, Cyber, you have a follow-up question, I'll be happy to answer that. But for now, let me make sure that y'all have access to our notes, because those can be useful. Anyone with the link can view. Let's switch back to chat. There we go. So yeah, so here is a PDF of our notes for today. We only added one page today on field alignment, but I think that it is actually a fairly useful drawing to have. So yeah, feel free to look at that if you ever get confused about how field alignment works. And if you're still confused on pointers, go back and look at the pointer pages. It's really, really good short reference to how pointers work in C. Okay, it's more than you understood in your course. Yeah, of course. Yeah, I'm happy to help. Yeah, I'm not knowledgeable about 100% of the C standard library, but I know most of it. So yeah, hopefully that'll help. And we'll be going through more of the standard library in the future. We'll talk about file I/O and console I/O. So yeah, we'll get there. So yeah. But all right, in that case, I am going to go ahead and take off for today. I hope that everyone enjoyed this lesson and was able to learn a lot. Oh, it's better than if it doesn't work. Here, have this. Yeah, sometimes, unfortunately, so I'm a TA for a course. I always make sure that I give my students the reason why we do things in addition to just do this thing. And I usually try and have students figure it out themselves, but something like this might not be something that you'd be able to figure out. So yeah, it's unfortunate that no one gave you an explanation as to buffering and why you might want to do that. But yeah, there you go. That's what random people on the internet are for, right? But anyway, yeah. Everybody take care. Have a wonderful day. I'll see you back here tomorrow, and we're going to talk about... We're actually going to write a data structure in C, so that'll be cool. We're going to learn about header files. We're going to learn about how we can structure a C project. We're going to learn about how to compile multiple files, and we'll be writing a dynamically sized array in C. So in other words, that's the equivalent to the C++ type vector, Java array list, that kind of growy, nice array type thing that you've probably been using for a while. That makes it so that we don't have to pre-declare the sizes of our data structures. So yeah, take care, everyone. Have a great day. I will see you tomorrow at noon Central. Bye-bye.